Chapter 8 examines a new set of reactions that actually compete with the substitution reactions. We call them elimination reactions. But let's begin by looking at an example of an SN2 reaction. So if you had your alkyl halide right here, that would be a primary alkyl halide. And of course, you have your nucleophile. It's a great nucleophile because it has a charge on it. We knew that the outcome of this reaction, an SN2 reaction, would be a substitution of the Br with the ethoxide ion. So in this case, you would have CH3, CH2, O, CH2, CH3, plus bromine as the leaving group. So again, this was your leaving group. And again, the reaction underwent an SN2 mechanism, making the product right here, which is an ether. Now, when we keep the same nucleophile and we change the halide in this case, instead of being a primary halide, if you take a look at this halide right here, this is tertiary. Again, this carbon is attached to 3 other carbons. Again, we have a great nucleophile. It's charged. Remember, the Na here is a spectator ion. We would expect, you've never encountered this, by the way, even in SN1. Remember, SN1 doesn't involve a strong nucleophile, it involves a weak nucleophile. And SN2 does not take place as a reaction. You actually get a different product. But first, let's actually look at what is happening here. What is happening instead is that you have your carbon right here where it's where the leaving group is attached. So that's your leaving group. That has a name, that carbon. That carbon is called an alpha carbon. The adjacent carbon, or carbons, since we have 3 of them here, those have a name. Those are called beta carbons. So alpha, beta, as in the Greek language. This hydrogen right here is called an alpha hydrogen. What happens here is that instead of an SN2 reaction, you actually get what we call an elimination reaction, where, pay attention to this, where you get this as the outcome. And I'm going to keep the alpha to show you what happened here. So an elimination meaning that the bromide ion, in this case, is your leaving group. Also, if you notice, this H was lost as well. So we say the beta H and Br minus lost. That's why we call it an elimination reactions. We will again describe what happens here. It may look like it's entirely new. Of course, it is entirely new, but of course, we will explain. So instead of a substitution, you actually eliminate two things. You eliminate the H and you eliminate the Br. And if you notice here, you're making a pi bond. You're making a pi bond. Of course, we have other materials in here. We are not that interested in them. I mean, these are byproducts. Like if you notice here, that H actually is right here, the one that's circled. So I'll put it in red so you can see it. But we will talk about the mechanism in depth. But that's the new type of reaction that we will examine in this chapter. A few things before we go on to the next video. An elimination reaction that involves the loss of two groups from adjacent carbons is called a beta elimination. So this process right here is called a beta elimination. Nucleophiles that are also strong bases promote the beta elimination reactions. And of course, the elimination is in competition with nucleophilic substitution for all alkyl halides with beta hydrogens. So that's the key, is that we're no longer just keeping things like, okay, this is a nucleophilic substitution. It has nothing to do with elimination. They are overlapping. So now you actually have more reactions competing against each other. It is noteworthy to discuss this, is that all elimination reactions involve the loss of elements from the starting material to form a new pi bond in the product. So if we take a look at this right here, we have a base now. We don't have a nucleophile. And if we notice that the H, the beta hydrogen, and the leaving group X are both lost right here. The base now is involved instead of a nucleophile, and watch again what is happening is you have a new pi bond, So what are the procedures to determine how to actually draw the elimination reaction? So we'll begin right away. The first thing you need to do is you need to find the alpha carbon. So the alpha carbon is where the leaving group is bonded. So if I have this, X, that would be my alpha carbon. The beta hydrogens are attached to beta carbons. So they are on the adjacent carbons. Meaning that you will not have, so this is your beta carbon, therefore this is a beta hydrogen, and this is a beta hydrogen. It is important to remember that you can't have a beta hydrogen on the alpha carbon, because that's sometimes a common mistake. So if you have an H supposedly on this one, then that's not a beta carbon. A beta hydrogen, I'm sorry. Not a beta hydrogen. So you identify all the beta carbons with the H atoms as we did here. and remove elements HX, HX from the alpha and beta carbons to form a pi bond. So what you are removing when you identify it is, let's say you remove this one and you remove that, and there has to be a pi bond in there. We will examine this more in depth when we get to the reactions of E1 and E2, but I'm just letting you know what would be the beta hydrogen and the alpha carbons in this case. While we're here, we would like to quickly just discuss what is happening in alkenes. Just remember that the product is an alkene because, again, you have right here a pi bond. Alkenes are sp2 hybridized. And of course, they have a trigonal planar geometry, which is again an angle of 120. So they are flat molecules. They are flat in the plane. Imagine they're in the plane of this paper. So if you, within this pi bond in the double bond, you have a, within the double bond, you have a sigma bond. So that's the sigma bond right there. And then, of course, outside of that, is the pi bond. This doesn't look like two pi bonds. This is only one pi bond. Let me make this a little bit more clear. Oops. So that's the sigma. Pi and pi. So of course the sigma bond electrons are closer to the nucleus. Again, means they are held more tightly. While, of course, the pi bond electrons are away or farther away from the nucleus. Are from far from nucleus. And of course, that means they are more loosely held. The whole point of this is that it's the pi bond electrons is more reactive. They are more reactive. Very well. What do we need to know from this? So just giving you some understanding here is that when we talk about elimination reactions, we always have to think about making, once again, making the most stable product or most stable alkene. And the key here is that the more substituted, more R groups, the more stable the alkene will be. So the stability of an alkene increases with the number of alkyl groups that are substituted on the carbon atoms in a double bond. So I'll give you an example. So if I have this, and I have methyls here, all of those are our groups. So this one is fully substituted, or as written below, tetra substituted. There are 4 groups. Whereas if I have this, okay, so this one is not fully substituted, but it's substituted. So again, the CH3 here is an R group. It's an alkyl group. It could be an ethyl, it could be a methyl, etc. And if you notice here, unsubstituted tends to have the highest energy. So this one would be the least stable. And of course, if you look down here, this would be the most stable. And lowest in energy. So monosubstituted look a lot more stable. Difference of between 2.7 kcal. If you look here, the cis, meaning you have 2 R groups now on the same side. If you have trans, is even more stable. Tri-substituted is very stable, and then tetra is the most stable. So the more R groups you have and the bigger they are, the more stable. So it's noteworthy to say that trans and cis is when they're both on the same side. And of course, trans is when they're on the opposite sides, same side. Opposite sides. So keep thinking of remembering we need more substituted alkenes for stability. Trans is even more stable, but the more substitution we have, the more stability we have for that sample or that compound.